So this is section 1.2 on vector spaces and affine spaces. And so a vector, so I maybe start with this. Remember that Rn is the set of all n-dimensional column vectors. So a vector X is this column of n numbers, usually put in parentheses. And I showed in this morning how you add, subtract, and multiply vectors by scalars. So what is called a subspace? So a vector subspace Rn is a set W of vectors. So this means this is a subset. Everything in W is a set of W is a set of vectors, which has three conditions satisfied. First of all, the zero vector. That's the vector where all the coordinates are zero, is in W. Second, W is closed under addition. This means that if X and Y are in W, then the sum of the vectors X plus Y is also in W. And the third property is W is closed under scalar multiplication. So if X is a vector in W and C is a scalar, a real number, then C times X is in W. And there's one very nice way to construct subspaces, and it comes from the notion of what is called a linear combination of vectors. So if x1, x2, up to x sub k are vectors, and c1 up to ck are scalars, then you can take a vector and multiply it by a scalar. So you can take the vector x1 and multiply it by c1. You can take the vector x2 and multiply it by c2. And in general, for each of these vectors, you multiply it by the corresponding scalar. Now these are just vectors again, and you can add them up. And this expression is what is called a linear combination of the vectors x1 up to x sub k. And there's a lemma that we prove. It's the first lemma in section 1.2. It says that a subset W of Rn is a vector subspace if and only if, that's what this double-headed arrow means, if and only if W is non-empty and closed under the operation of taking linear combinations. So again, in 300 level math classes, we have to learn how to give proofs. So suppose that, so let's prove that in this direction. If W is a vector subspace, then it has these properties. So suppose W is a vector subspace. Then the zero vector is in W, because that was the first condition for a subspace. So W is non-empty. A set is empty if it doesn't contain anything, and W has to contain zero, so it's not empty. And if X and Y let's see. So we have to show that must show W is closed under the operation of taking linear combinations. Right. So again, this has to be strange if you haven't seen proofs before, but that just means you have to spend a lot of time trying to understand how you do this kind of mathematical reasoning. So remember the definition of a linear combination. You have k vectors, x1, x2, up to x sub k. You multiply each of them by a scalar, and then you add this whole collection up, and that's what's called a linear combination. And I have to show every linear combination is contained in W. So we're going to prove this by what is called mathematical induction. So this is an important method to prove things in all of mathematics. Let's consider just k equal 1. So consider this is a linear combination of k vectors. Suppose k is 1. You just have c1x1. So, but if W is a vector subspace, then if x1 is in W and c1 is a scalar, that means a real number, then W is closed under scalar multiplication, so c1x1 is in W. So every linear combination that involves only one vector is in W. Suppose we look at the case k equal 2. So you have vectors x1, x2 in W, and scalars c1 and c2. So because W is a subspace, c1x1 is in W. And because W is a subspace, c2x2 is in W. The reason is subspaces are closed under scalar multiplication. But if these two vectors are in W, c1x1 plus c2x2 is in W, because vector subspaces are closed under vector addition. So that says that every linear combination of two vectors is in W. And I could prove it for 3 and I could prove it for 4, but I can't go on forever, right? We're only alive for a finite amount of time. So the way you prove something by induction is the following. Suppose K is greater than or equal to 2, and assume every linear combination of K vectors is in W. What we have to prove is every linear combination of K plus 1 vectors is in W. So how do we do that? Suppose we have K plus 1 vectors, and we have K plus 1 scalars. By the induction hypothesis, that's the statement that every linear combination of K vectors is in W. If we just look at this set of K vectors and K scalars, C1x1 plus C2x2 up to CKxK is in W. And because W is closed under scalar multiplication, we also have that CK plus 1 times WK plus 1 is in W. And then you just use the fact that W is also closed under vector addition. So when you add these vectors, you get C1x1 plus C2x2 plus CKxK plus CK plus 1, BK plus 1 is in W. So we proved that every linear combination of one vector is in W, and we proved that every linear combination of two vectors is in W. And I just showed that if every linear combination of K vectors is in W, the same is true for K plus 1. So if you let K equal 2, because it's true for 2, it's true for 3. So every linear combination of 3 vectors is in W. But if it's true for 3, it's true for 4. And if it's true for 4, it's true for 5, and so on forever. And that's why this is a proof that is true for all K. And this strategy, this method of proof, is called mathematical induction. And it really is a good investment of your time to think very hard about this and understand what's going on. Okay. The proof in the opposite direction is much easier. If a set of vectors is non-empty and closed under scalar multiplication, if it contains any vector, you multiply it by the scalar 0, you get the 0 vector, and there's not much else to do. So you have to think about it, or I wrote out the proof in the notes, and you can find it there on page 12. And as a corollary of this, we have another lemma, which in the notes is 1.3, lemma 1.3. The set of all linear combinations of a non-empty finite set of vectors is a vector subspace. Because if you take the linear combination with all the scalars equal to 0, you get the 0 vector. And if you take two linear combinations and add them, you just get a bigger linear combination. So there's really not very much to prove about that. Let me just do a few calculations to show you very concretely what a linear combination is. So let's see if I had done this. Suppose I take the vector x equal to 2, 3, and y equal to 7 minus 1. And I could take the linear combination. This is just an example. 5 times the vector 2, 3 plus minus 3 times the vector 7 minus 1. So you do things step by step. When you scale or multiply a vector by a number, you multiply every coordinate by the number. So 5 times the vector 2, 3 is the vector 10, 15. And minus 3 times the vector 7 minus 1. Minus 3 times 7 is minus 21. Minus 3 times minus 1 is plus 3. And then when you add, 10 minus 21 is minus 11. And 15 plus 3 is 18. So here we have a linear combination of two vectors equal to this. So just to double check that you can do this sort of thing, suppose I take the vectors 1, 2, 3, 4, 5, 6, 7, 8, 9, and I take 2 times this minus 3 times this plus, I don't know, I'll make this 4 times this plus 2 times that. So you should do the calculation. Compute this vector. This will be a vector in R3 because these are 3-dimensional vectors. This vector times 4 minus this vector times 3 plus this vector times 2. So do the calculation and tell me what you get. Right. So let's see. Anyone get an answer? Can someone tell me what the vector is? Let's see. 4 times the vector 1, 2, 3 is 4, 8, 12. Minus 3 times this, that's 12, 15, 18. Plus 2 times this is 14, 16, 18. So this minus this vector minus this vector, 4 minus 12 is minus 8. 8 minus 15 is minus 7. 12 minus 18 is minus 6. Plus this, 14, 16, 18. Minus 8 plus 14 is 6. Minus 7 plus 16 is 9. Minus 6 plus 18 is 12. So this vector is equal to this vector in R3. right? It's just doing a little bit of arithmetic. Suppose I have 2, 0, minus 1, 7, 1, minus 4, 3, 2, 8. And suppose I take 1 times this, plus 2 times this, plus 3 times this. So do the calculation and tell me what you get.
Is that a -9 with the 7, 1?
7, 1, minus 4.
Okay.
What's 1 times the vector 2, 0, minus 1? It's just 2, 0, minus 1. What's 2 times this vector?
14.
Just multiply every coordinate by 2. What's 3 times this? Multiply every coordinate by 3. 9, 6, 24. You add 2 plus 14, 16, plus 9 is 25. 0 plus 2 plus 6 is 8. Minus 1 minus 8 is minus 9. Plus 24 is 15. So if I did my arithmetic correctly, this linear combination of 3 vectors is equal to this. Okay. Now let me show you the connection between homogeneous linear equations and vector subspaces. Let's take an example. Say 3x1 minus 2x2 plus x3 equals 0. So we want to find the solution space. That is the set of all solutions. So you could, for example, write x3 in terms of x1 and x2. So x3 is minus 3x1 minus 2x2. Oops. Sorry, if I bring this on the other side, x3 is minus 3x1 plus 2x2. So if I take any value for x1 and any value for x2, x3 has to be this. So this is x1, x2, and my x3 is minus 3x1 plus 2x2. And I'm going to show this set of vectors, all the vectors of this form, is a certain vector subspace. Let me just write this as x1 plus 0, 0 plus x2, minus 3x1 plus 2x2. You never have to do this. I'm doing this just to make clear what's going on. This vector is a sum of 2 vectors, x1, 0, minus 3x1, and 0, x2, 2x2. And this is just x1 times the vector 1, 0, minus 3. And this is x2 times the vector 0, 1, 2. So the solution space means the set of all vectors which solve the equation 3x1 minus 2x2 plus x3 equals 0 is, I'll call it W, it's the set of all vectors of the form x1 times 1, 0, minus 3 plus x2 times 0, 1, and 2, where x and 1 and x2 can be any scalars whatsoever. And what this is the set of all linear combinations of the two vectors 1, 0, minus 3 and 0, 1, 2. And the set of all linear combinations of a finite set of vectors we saw was a subspace. So this is the solution space of this equation. It's a vector subspace in R3. All linear combinations of these two vectors. So this is an example of a general result, which is the first things in this chapter so far that's worthy enough to be called a theorem. So this is theorem 1.1. It says that the solution space of a homogeneous linear equation in n variables is a vector space, is a vector subspace of Rn. And the proof goes as follows. Suppose this is our equation, a1x1 plus a2x2 plus a3x3, and so on. They're n variables. And a homogeneous means the right-hand side is 0. So observe, a1 times 0, if I let all the x's equal 0, a2 times 0, and so on, that's just adding up a bunch of zeros, and that's 0. So the 0 vector, I'll call this, let's say, let W be the solution space. All vectors in Rn that solve the equation. The 0 vector is in W. If we have two vectors, x1 up to xn and y1 up to yn are in W, what does that mean? It means that each is a solution of this equation. So a1x1 plus a2x2 up to an xn is 0. And the same for the y's, a1 y1 plus a2 y2 plus an yn is 0. And add these equations. You get a1 times x1 plus y1 plus a2 times x2 plus y2 all the way up to an times xn plus yn equals 0. So therefore, the sum of these two vectors, which you get by adding coordinates, is in W. So W is closed under vector addition. And if I take this equation and I multiply it by C, I get CA1x plus CA2x2 plus CANxn equals 0. So the vector CX1, CX2, CXn, which is C times the vector x1, x2 down to xn, this is also in W. So if I look at all the vectors that solve this equation, it contains the 0 vector because the equation is homogeneous. And it's closed under vector addition, and it's closed under scalar multiplication. So the solution space is a vector subspace. Right? That's a really, really, really important fact. Now we can ask, what about inhomogeneous equations? So, I mean, what's an example of an inhomogeneous equation? Maybe 2x plus 3y equals 11. This is inhomogeneous because the right-hand side isn't 0. And notice that 2 times 0 plus 3 times 0 is 0. It's definitely not 11. So the 0 vector is not in the solution space. So the solution space is not a vector subspace for this inhomogeneous equation. In fact, it never is. But it's something very close to a vector subspace. It's what is called an affine subspace. So we have to know, what is the translation of a set, or the shifting or the movement of a set. Translation of a set by a vector. So if V is a vector in Rn, and X is a subset of Rn, so this is a vector, and this is a subset of vectors. We can define the translate V plus X. This means you just look at all vectors X in X and translate or move them by V. So this is V plus little x, and you can add vectors for all X and X. So this is what is called a translation of the set X by the vector V. And an affine subspace of a vector space, or of the vector space Rn, is a set of the form L equals V plus W, where W is a vector subspace. So an affine subspace is what you get by taking a vector subspace and translating everything in W by some fixed vector V. And the important theorem for an inhomogeneous equation is the following. This is the second theorem in this chapter. The set L of solutions of the inhomogeneous equation a1x1 plus a2x2 and so on up to anxn equals b is an affine subspace. And the proof is really very interesting. So, proof. Let's make it a non-zero homogeneous equation, inhomogeneous equation. So, by a lemma earlier in the chapter in section 1.1, every non-zero inhomogeneous equation has a solution. And if V is a vector, V1 up to Vn, is a solution, that means that A1 V1 plus A2 V2 and so forth up to AN Vn is equal to B. That's what it means for this to be a solution. Now, we can consider the associated non-zero homogeneous equation What is it? Well, it's the same equation, but with a zero on the right-hand side. A1x1 plus A2x2 up to AN xn equals 0. And let W be the solution space of this equation. So what can we say? We can say the following. If x1 up to xn is in W, then a1x1 plus a2x2 up to an xn is 0. But also, this vector v is a solution of the inhomogeneous equation. It's an L. So a1 v1 plus a2 v2 up to an vn is equal to b. And now we add the equations. We get a1 times v1 plus x1 plus a2 times v2 plus x2 up to a sub n vn plus xn equals b plus 0. In other words, the vector v plus x, that's v1 up to vn plus x1 up to xn, is in L for all x in W, which means to translate v plus w is contained in L. Now I want to show that these two sets are actually the same, so that L is V plus a subspace, and therefore L is an affine subspace. So how can we prove that? Well, one way is the following. Suppose that V prime with coordinates V1 to V1 prime to Vn prime, and V with coordinates V1 up to Vn are both in L. That means A1 V1 prime plus A2 V2 prime up to AN Vn prime is equal to B, and A1 V1 plus A2 V2 plus AN Vn is equal to B. And now I take these equations and I subtract them. So I get A1 V1 prime minus V1 plus A2 V2 prime minus V2 and so forth, plus AN Vn prime minus Vn is equal to B minus B, or 0. So that means that the vector V prime minus V, which is V1 prime down to Vn prime in coordinates, minus V1 down to Vn in coordinates, is equal to some vector W in the solution space of the homogeneous equation. So if V prime minus V is equal to W, then V prime is V plus W, which means that every vector in L can be written as V plus something in W is contained in V plus W. And now I look at these two set relations. V plus W is contained in L. L is contained in V plus W. When you put that together, that says V plus W equals L. So L is an affine subspace. And that finishes the proof of the theorem. So the important little lesson in what we just did is that the set of solutions of a homogeneous linear equation is always a vector subspace, and the set of solutions of an inhomogeneous linear equation is always an affine subspace. And these are geometrically very interesting objects, and we're going to spend a lot more time studying them. But what I just did is cover section 1.2, and what I like to do is cover exactly one section from the book in each of these sort of little classes. But again, it's completely optional to attend or not to attend. And everything is recorded and will be posted on YouTube. So this is section 1.1, exercise 5. So in R3, there are three sort of special vectors. E1, which is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. So, you can think of an ordinary three-dimensional space. You have the XY, x-axis, y-axis, z-axis. If you go like 1 unit in the x direction, this vector has coordinates 1, 0, 0. This is the vector E1. If you go 1 unit in the y direction, that's the vector E2. And if you go 1 unit in the z direction, that's the vector E3. So just, you don't need this to do the problem, but just, it's always good to have pictures of things. And geometrically, a three-dimensional vector is just a vector in ordinary three-dimensional space. And these are the unit vectors in the positive direction on each axis. So suppose I take a vector x1, x2, x3. I want to write it as a linear combination of these three vectors. So I could say, just using vector addition, this is x1, 0, 0, plus 0, x2, 0, plus 0, 0, x3. Because if I add these three vectors, this is what I get. Right? Is that okay?
Yes.
And of course, this is just like x1 times the vector 1, 0, 0. And this is x2 times the vector 0, 1, 0. And this is x3 times the vector 0, 0, 1. And these are the vectors e1, e2, e3. This is x1, e1 plus x2, e2 plus x3, e3. So this is a linear combination of e1, e2, e3. So this says I've expressed this vector as a linear combination of x1, x2, x3. And then I want to show that it's unique. There's no other way to do it. So if the vector x1, x2, x3 is some linear combination, let's say a e1 plus b e2 plus c e3, for some scalars a, b, and c, a e1 is a times 1, 0, 0. And b e2 is b times 0, 1, 0. And c e3, c times 0, 0, 1. And when I do the scalar multiplication and add, I get the vector ABC. And this vector equals this vector if and only if A equals x1, B equals x2, C equals x3, because vectors are the same only when they have exactly the same coordinates. So the only way to write x1, x2, x3 is a linear combination of these unit vectors is like this. So this proves uniqueness. This proves existence, that there is a way to write this vector as a linear combination. This says there's only one way. It's unique.
And where can we find like how to do the proofs?
Thinking. I mean,
oh, so there's no like actual way, like there, like it's not like how like you do in high school, like those kinds of proofs where like they tell you what kinds of proofs they are or nothing,
yeah.
Right?
So what you have to do is study the proofs in the text and be able to use the ideas in a proof you've seen to solve other problems, to give other proofs. I'm not always going to ask you to prove something that was proved in the book. I'll often ask you to prove something you haven't seen before, but that should be easy to prove using techniques that have already been used a lot in the book.
Okay, thank you.
Sure.
Professor?
Yeah.
So one question. So if we submit the homework and then we get it wrong, so do we still get like the credit or not?
Yes. Yeah, I mean, with the homework, it's more that I want you to be doing problems constantly. And if you haven't done all the problems or if you make mistakes, it's okay. At least you're working at it. And you get a little bit of credit. I mean, every homework counts towards your final grade, but you usually get full credit if you've just done a significant, not even all the problems, but if there's something substantial in your paper, usually it's like 1 point for each lesson. So a homework is typically worth 2 points out of 20. Actually, there's extra credit for the homework. But yeah, I mean, the only way you learn algebra or any other kind of mathematics is by doing a lot of problems. So that's the reason I have you turn in the homework is, and give credit for the homework, is to give you a reason to do a lot of problems.
All right, thank you.
I have one more question. So what we just learned right now, that is what's gonna help us answer the other questions on page 20, correct?
Well, everything.
I'm just trying to figure out, because like basically what I just want to figure out is the morning session is going to be like for one lesson, and then the afternoon session is going to be for another lesson.
Yes, exactly.
Okay. Okay, thank you.
Because basically I cover 2 sections a day, and I do one in the morning and one in the afternoon. But again, there's students who are working. They can't come to any of the sessions. That's why everything is videotaped and posted on the YouTube channel.
Okay, thank you.
All right. Sure. Anything else for today?
Will there, sorry, will there be office hours?
Sorry, will there be what?
Office hours?
That's what this is.
Oh, okay.
I mean, this is sort of a combination of, you know, a class, but this is an asynchronous class. That means that it's not required for any student to come to any of these classes. I mean, I could be taping these lectures by myself, you know, without any students, without anybody online, but I think it's advantageous if you can come to one of these sessions to listen to the lecture and ask questions about it as I'm doing it. And I also will have additional hours, like office hours, if you like, if you have questions that don't fit into, or if you can't attend one of these sessions. And I said, you just have to send me an email and I'll set up a time for you. But these 2 hours a day are like the office hours also. That's the whole point of being available online.
Okay, thank you.
What I don't know is whether it is reasonable to also have some hours over the weekend, because normally you shouldn't require anyone to have to like go to a class on a weekend. But I might just make myself available at some time for anyone who has a question, especially people who are working all day and can't come to any of these sessions. Because some people work, you know, like 9 to 5 or 8 to 6 and just can't make one of these classes at all. Okay. If that's it, then we will quit for the day and I'll be back at 10 o'clock tomorrow. All right. Bye all.